everyone, it looks like we've lost Garance, which is unfortunate, but good evening and welcome to the 19th Annual Caithness International Science Festival. We're delighted to welcome you tonight at this, the first of 3 events from Caithness Astronomy Group that are going to help us get to know our celestial neighbour, the Moon, a little better. I'm Nicola MacLeod, the Festival Coordinator, and joining us from Caithness Astronomy Group are Gordon Mackie, who will deliver the featured presentation, Neil McLean and Christian Wilhelm, who, weather permitting, will be carrying out the live observations. However, that's not looking very likely this evening. John Hilton and Ian Darby are here to help moderate and assist with the Q&A. Before we begin, a little bit of housekeeping. This event is being recorded, however your screens are not. This has been a popular event, so please direct all comments and questions through the Q&A box and we'll try and answer as many as we can. As an audience, you can upvote questions, so if there's a question someone else has asked that you're keen to hear the answer to, then give it a thumbs up to move it up the list. I'm now going to hand over to Gordon Mackie for tonight's presentation, The Moon, Part 1. Looking at the Moon, what can I see?
That's great, thank you, Nicola. I'll just mention the other member of Caithness Astronomy Group that we have with us tonight is Professor Keith Nicholson. Keith is actually going to have a quiet night tonight until the Q&A start, and he's actually going to be giving the presentation on Sunday evening. Let me just share my screen and we'll begin with the presentation. I get a thumbs up from a few folk if you're seeing the presentation. Excellent. So it's great to be able to contribute again to the Science Festival events this year, and what we're going to be doing over the next 3 nights is telling you a little bit about our celestial neighbour, the Moon. And the 3 main topics that we're going to cover is, first of all, tonight I'll be giving a short talk on looking at the Moon, what can I see? Then tomorrow I'll be talking a bit about the Moon in motion, so explaining why we see phases of the Moon, why eclipses happen, and other things like that that are linked with the movement of the Moon round about the Earth. And then on Sunday, Professor Keith Nicholson, member of Caithness Astronomy Group, will be talking about the part of the Moon that we don't get to see from the Earth, the far side of the Moon. Each night we'll end with a short Q&A session. And the plan was, if the weather permits, for us to do live streamed telescopic observations of the Moon each evening as well. Now, unfortunately, tonight there's one big cloud covering the whole of Caithness by the looks of things from the satellite image, so we won't be doing the live streamed observations of the Moon. So tonight, Neil and Christian are able to join us from indoors, which is good. And the other 2 gentlemen that are there in the background helping out this evening are Ian and John, and I'm delighted to see that Keith has joined us as well. So I'm hoping that with all of those brains combined together, if there's any questions later on that are too difficult for me, they'll have the answer. And feeling that, I'm sure there's enough fingers there that they can be typing into Google to help out. So tonight we're going to be talking about what can you see when you look at the Moon. So when you look up at the Moon in the night sky, what is it you see? Well, as you can see from the photograph in the top right of the slide here, the most obvious thing is that there are dark areas and much lighter areas. So even with the naked eye, you can make out the dark patches and the lighter patches. And if you have a bit of a good imagination, as many people have done over the years, they may be able to see shapes in there that perhaps look like the man in the moon, or the profile of somebody's head on the moon. I have to admit, whenever I look at the moon, I can never make out any of these sort of shapes. However, there is one that, even to my head lacking perhaps a bit of imagination, there is one that I can always see when there's a full moon. So have a look at this image of the full moon there, and I'm going to ask the question, can you see the Easter bunny? So this is quite topical, because obviously we're coming up to Easter in a few weeks' time. Can you see the Easter bunny? So let me help. I'm going to show you something that may assist. Now, when you have a look at the image on the right-hand side of the full moon, can you make out the Easter bunny? So I would encourage you, there will be a full moon in just over a week's time. And if you get some clear skies, go out, have a look and see whether you can spot the Easter bunny on the moon. So what's the moon made of? Well, unlike in the Aardman animations, it's not made out of cheese. It is made out of rock. So we have a rocky surface with not really much else. It's a desolate, barren, rocky world. There's no water, there's no trees, no animals scurrying about the surface, no sign of any clangers hiding in craters, anything like that. What you have is a barren, rocky surface that is mostly large chunks of rock covered with very fine powdery rock that's essentially the lunar soil, and it's got a special name. It's called regolith, and as you can see on this astronaut's spacesuit, the outside of it, it does seem to get everywhere. It clings to the spacesuit as they walk across the surface. So it is quite fine, messy material, but that's the lunar soil. But it's not really the same as the sort of soil that we have on the Earth, because it's essentially pulverized rock from millions or billions of years of massive impacts on the surface of the moon. So if we've had lots of impacts on the surface of the moon, we should be able to see the impact scars. And when you look at this image of the moon, most of the prominent features that you can see excuse me, are actually a result of significant impacts on the lunar surface. So let's have a look at a few of them. The darker areas are essentially lava-filled basins. So it's very large flat areas where lava has flooded the basin and generated a relatively flat surface, which is this fairly dark colour in comparison to the rest of the lunar surface, and it stands out to the naked eye. Now, a long time ago, when people were observing the moon, they saw these dark patches and they imagined that there must be seas or oceans on the surface of the moon, because they hadn't sent spacecraft there hundreds of years ago. There was no way for them to know that it was just lava plains rather than water on the surface of the moon. Now, these areas are referred to as lunar mare, or Maria is the plural, and they are the results of extremely energetic impacts, large impacts on the surface of the moon. And sometimes what you'll find round about these large impacts, round about these impact basins, are mountain ridges, mountain ranges. And there's a very prominent one here that we'll look at in a bit of detail a few slides on. And as I said, they quite often found round about impact basins, or sometimes round about the larger impact craters. And you'll see a couple identified here. And impact craters are essentially the same as the impact basins, except it's just a smaller chunk of rock has hit the surface, and it hasn't caused as much catastrophic damage on the surface of the moon. So you can see there's craters there. And the last thing I want to point out on this slide is that round about the large impact craters, you'll see radial streaks coming out from the crater. So if we pick this one at the bottom, this crater here called Tycho, you can probably see bright lines stretching out from the crater in lots of directions. And what that is the material that's been blasted out from the impact has spread out across the surface of the nearby surface of the moon. If we have a look at this crater here, which is Copernicus, and we'll see in a bit more detail shortly, you can see again round about the bright impact crater, you've got material that has spread out as a result of being flung out from the impact zone itself. So there's the obvious impact scars that you can see on the moon. Certainly you can see that the lunar mare, these dark zones with the naked eye, you will probably need binoculars to be able to spot the predominantly the craters and the ejecta rays and the mountain ridges. But you don't need much more than binoculars. So you don't need a big fancy telescope. You can see a lot of these features just with binoculars and with some other basic equipment that I'll talk about later. A lot of the coming slides are going to concentrate on the detail in this particular zone. And the reason I've selected it is because there's a lot of different types of impact scars there. So that's the part we're going to look at for a number of slides, just looking at the different features in more detail. But before we move on to that, I just want to mention a little bit about the naming of features on the moon. The features started to get named a good few hundred years ago, once we had telescopes and people were able to start discerning different things on the disk of the moon. They started to name them, and what you've got is the lunar mare are generally Latin terms describing weather and other abstract concepts. So you've got things like the sea of showers, the sea of rain, sea of tranquility. I'm sure many of you will know that one. Sea of nectar, ocean of storms. So there's a range of different names for the large impact basins, and then for the large craters, the very obvious ones, they're generally named after the deceased scientists, scholars, artists. So if you look at the orange text here, you'll probably recognise some Greek scholars and famous astronomers in it. You've got Plato, Copernicus, Aristarchus, Kepler, Tycho. So that's the basis behind the names. Some of the smaller features have been named in more recent times, and you'll not be surprised to hear that a few craters round about the Apollo 11 landing site, for instance, have been named Armstrong, Aldrin and Collins for pretty obvious reasons, I think. So how are the craters formed? Well, there are three different stages to the generation of a crater. The precursor to that is obviously you need to have a big chunk of space rock traveling at high speed through space in the direction of the rocky body it's going to impact. So in this case, it's the moon, but there are impacts like this happen on the Earth and on the other planets and asteroids, rocky asteroids in the solar system. So it's not only the moon that sees this. The difference is there's no weather or geology on the moon. So any impacts happening over recent times, and I mean the last few billion years, are still there, clearly obvious to see. So you've got this space rock traveling through space at perhaps tens of kilometers per second. So that's per second, not per hour, tens of kilometers per second, so extremely fast. And if it hits the surface of the moon, what happens is the rock is very quickly severely compressed, and essentially the energy imparted on the rocky surface causes a lot of material to be blasted out from that impact zone. So you've got a bit of excavation. So in other words, it generates a big hole in the surface of the moon, and depending on the size of the impact crater, it may be a bit unstable, and there will be later modification will happen when the sides or the base of the impact crater settle down after the impact. Now, when I say later, all of this happens in seconds. So we're not talking about a crater taking years or even hours to form. It's seconds we're talking about for these sort of things to happen. So it is a very, very rapid process. So that was a bit of an overview. I've got a couple of animations here that might help you visualize what's happening during impacts and why the craters on the moon don't all look essentially the same. So let's have a look at the image on the right-hand side. And what you'll be able to see is this arrow here is pointing to two relatively small craters when you compare it with some of the other large craters in the image. And I think you'll be able to see straight away that the smaller craters do look quite a bit different from the larger ones. So let's just play this animation and let you watch it. But essentially the smaller craters are caused by smaller rocks impacting the surface. So they have a little bit less energy. So let's have a look what happens with a small impactor. So you see the impact there, material being thrown out and a crater being left behind as a result. So you've got the dip in the surface, the ejected material thrown out, and the crater for a relatively small impact is just a basic dish shape. So if you have a crater that on the moon is kind of 20 kilometers or less, then that's the typical shape that you get from the impact. However, if you have a much more energetic impact with a larger impactor, the final modification stage can lead to the crater looking a bit different. So let's have a look at what happens. So you can see the end result here. You have terraced slopes to the rim of the crater. You have peaks in the center floor of the crater. And I think you can probably see that from the photograph at the bottom of the screen. You can see the central peaks in the middle on the floor of the crater, and clearly the rim of the crater has got some sort of terraced feature to it. So let me just play that again, and this time I want you to watch what's happening that forms the central peak. Essentially, the crust is rebounding from the impact, and that's what forms the peak in the middle of the crater. So because it's so energetic, it has a slightly different end result. So I've put these the still image here really just in case the videos didn't work based on previous experience. So it's not really showing anything different, but you can definitely see the terracing on the walls of the more complex crater and the central peak there. Now, this crater here, Copernicus, is about the same size as this one, which I think is Archimedes, and this one up here is Plato. So they're all similar size and all definitely large craters. So why is this one different from these? So you can actually see, here's a close-up image from the Lunar Reconnaissance Orbiter of Copernicus, and here's a close-up of Archimedes. So you can probably see that the rim of the crater looks roughly similar. There's sort of a terracing effect around the rim, but there's no central peak here. So why are they different? Well, the answer is that in the case of these craters here, which have a nice flat floor, it's because the impact led to cracks in the crust that allowed the bottom of the crater to infill with lava. And that lava then, once it had infilled, it cooled and solidified, hiding the original crater floor and any central peak. So they're formed by the same process. The only difference is that the impact for these craters was sufficient that it led to lava coming up from below the crust and infilling a large proportion of the crater. So let's talk about when you get the really, really big impacts that generate the impact basins. So here we've got Mare Imbrium, which is the, I think, is it Sea of Showers, or I keep mixing them up, but I think that's what it is. And what's happened is, hopefully, if I mark out what was the rim of the impact crater, you've got an enormous impact zone here. And the impact was sufficient that it cracked the crust, allowing lots of lava to feed up and infill the impact basin. So what you would have had here was what you're seeing, a sort of terraced impact basin, possibly with central peak, but because the crust was damaged sufficiently to allow lots of lava to feed up to the surface, you ended up with this lava plain here that now forms what's referred to as a lunar sea or lunar mare. So that's how the all of these large impact basins, the dark zones on the moon, when you look at it with the naked eye, how they were formed. And as I mentioned earlier, quite often you'll see mountain chains or mountain ridges along the edge of the impact basins. So this ridge here is the Montes Apenninus. So the height of these mountains above the surrounding area is roughly the same height as the Alps in Europe. Now, I read the other day, and I just find this quite mind-blowing, that if you think about it, the Alps and the Himalayas are all formed on the Earth by the crust pushing up and forming the mountains, and it takes millions of years for that to happen. But these mountains here were formed in a matter of seconds during an impact on the moon a few billion years ago. So you've got mountains the size of the Alps generated in a matter of seconds. So it's quite amazing thinking about that and the amount of energy that would have been involved to cause it. And to give you an idea of the scale, the Mare Imbrium it's got a diameter roughly the same as the distance from the north of Scotland to the south of England. So we're talking, what's that, about 600 miles. Just over 1,000 kilometres in diameter for the Mare Imbrium. They've calculated the impact of the lump of rock that caused the impact basin would have been about 250 kilometres. So to give you an idea, the one that they believe led to the dinosaurs becoming extinct, they reckon that that impact of that asteroid was about 10 kilometres in diameter. So it was probably just as well there was no life on the moon when these impacts were happening, because they were extremely devastating and energetic. And all of that happened about 4 billion years ago. Now, obviously, the crater Copernicus is a bit smaller. It looks small in the photograph, but it's actually quite large. It's 93 kilometres in diameter. It's almost 4 kilometres deep. It was probably caused by an impact at about 7 kilometres in diameter, so not that much smaller than the one that hit the Earth, and probably led to the demise of the dinosaurs. And the central peak here is about 1 kilometre high. So let's take that in relation to things in Scotland you might be able to compare it with. So Ben Nevis is 1.4 kilometres high, so the central peak isn't far off the size of Ben Nevis. And if we look at the diameter of the crater, if you were to stand on Dunnet Head, and that was one edge of the crater, the other edge, the opposite edge of the crater, would be around about Cape Wrath. So there's no doubt, although it looks quite small in the photograph, it's really quite a significant impact zone on the moon. So if you like to think about these kind of things and you like to do a little bit of experimenting, then you could take a trip down to the beach and have a go with some rocks on the sand, but you're not going to manage to get the equivalent of 10 kilometres or 20 kilometres per second impact speed. It's really what you have to do is a bit of modelling or simulations on a computer. And for those that are interested in having a little play themselves, there is a website that has an impact simulator where you can change variables, change the size of the impactor, the angle of impact, the speed that it comes in at, the type of rock that the impactor is made of, the type of rock that it hits, and what you'll get as the output is the size of the crater, the depth, and you can compare it with places on Earth to give an idea of how big or how extensive the crater would be on Earth from that size of rock hitting the surface. So you can have a little bit of experimenting yourself there. And it's fairly simple to do, so it's probably suitable for school kids to have a go as well. Okay, let's talk about the Terminator. Now, I don't mean this guy here from the film decades ago. I'm talking about the lunar Terminator. And the lunar Terminator is the boundary between day and night on the surface of the moon. So if you look at the orange drawn arcs on the moon there, the edge of the sunlit zone is obviously the boundary between the daylight side and the nighttime side, which is, so here in the crescent moon, you've got the daylight side, and the nighttime side here is in darkness. So why are we talking about the Terminator? Well, the simple reason is that the Terminator is where the shadows will reveal surface details of structures on the moon. So if you have a look at the bit here that's quite far from the Terminator, there's not an awful lot of detail on the surface. However, if you look along the edge of the terminator, because there has been shadows cast, it gives an idea of what the relief is, what the surface of the moon is like there. So for observers of the moon, the terminator is quite important. And the good news is that from one day to the next, the terminator moves position. So from one night to the next, you'll have different parts of the moon will be best for viewing through a telescope. So here's an example here. If you have a look at the full moon, you can see those features are prominent, such as the ejector rays. They tend to stand out best in the full moon when the sunlight is shining directly onto them. Whereas near the terminator, so here's the terminator zone here on the left, you can see that the shadows are revealing the shape of the craters, the location of the mountains and the like. And if you compare that with the full moon, that information is not available visibly during the full moon phase. So observational astronomers like the terminator because that allows them to see extra detail when they're observing through binoculars or a telescope. So here's a couple of photographs taken, I think 2 days apart, and they're showing the same craters. So you can see the crater here, Tycho, and here it is in the other image, and the large crater Clavius, and again in the other image. And when you look at the two of them, you can see they look quite a bit different, all down to the angle that the sunlight is hitting the craters. Here's another example I want to talk a little bit about. So what the shallow angle of sunlight does is it gives the surface of the moon a three-dimensional feel. It doesn't appear flat like it does in the full moon phase. You can actually start to pick out the shape of the surface features, and it is possible. So if we look at this close-up of the crater Plato, you can actually see the shape of the shadows, which gives an idea of the shape of the rim of the crater. And the other thing you can do is, with the shape and size of the shadows, with a bit of simple trigonometry, you can actually calculate what the height of these features are. So there's a lot of information that can be obtained just from fairly basic observations of the lunar surface from the Earth. So at this point, I would normally be handing over to Neil and Christian to give some live views of the moon, but obviously that's not happening tonight. So I've got a few slides just to give you a flavour of the sort of things that may have been visible. But before we start, here's the telescope that Christian would use for it. With any luck tomorrow, the forecast is looking a bit better, so we may be able to get some live observations done. But just to show you, it's not a big telescope, but it is a telescope with a fairly long focal length, which allows detailed views of the moon. Now, in January, we did a trial run and we live streamed views of the moon from my back garden in Thurso. So this is the telescope I used at the time, and there's a screen capture from the live view of the moon back in January. So that sort of thing will hopefully be visible tomorrow night. Now that's a kind of wide angle view. We'll probably get a closer up view of that tomorrow if the clouds clear. For those of you that don't have sophisticated equipment, don't worry, you can actually get a decent photograph of the moon just using your camera phone. And if you hold it up to the eyepiece of a telescope or even a bird spotting scope or a pair of binoculars, you should be able to get a photograph of the moon through it. It can be a bit fiddly, but if you persevere, the photograph on the left-hand side is the photograph that was taken with the arrangement that you can see on the right, just by holding the phone up to the eyepiece. And the little video clip that you saw in the bottom there, that's actually video footage of the moon taken with a zoom lens on a digital SLR camera. So you can see with equipment that a lot of people may well have, you can manage to get some nice detailed photos and views of the moon that way. To observe the moon, like I said, binoculars or a telescope will give you tremendous detail of the surface. So this is a photograph of the moon that I took end of last year, and you can see that the lunar mare stand out. There's lots of craters. It is really clear. So any kind of telescope will give a nice detailed view of the moon. Binoculars will show some of the larger features. So if you get the chance, have a look at the moon. It doesn't disappoint. But try and pick a time other than full moon so that you can look at the detail along the terminator. If you want to know what you're looking at, you probably want a lunar atlas, and you can get apps these days. You can buy paper atlases, but one of the most detailed ones that I've come across is a free software atlas that you can download, and you can essentially click on the different parts of the moon and it'll tell you all about them. So I would recommend that you, if you're keen on learning about the different features on the moon, that's well worth a look. And on the right hand side here is what the moon would look like tonight if the sky was clear. So it would look roughly like that. And this is a simulated view from this virtual moon atlas. So let's pick out a few of the features that would be visible. And the most obvious one that everybody's interested in is, where did Apollo 11 land? Where did the first men land on the moon? And obviously it was in the Sea of Tranquility, and it was on the it was on the southern parts of the Sea of Tranquility. And here's a photograph I've taken. You can't actually see the remnants of the lunar lander or the astronauts' footprints here. You can't even see that with the Hubble Space Telescope. But what you can pick out is a small crater. It's about 5 kilometers in diameter, and that's Armstrong crater. So it's one of the craters nearby the Apollo 11 landing site in the Sea of Tranquility. Other mare that stand out quite clearly just now are the Mare Crisium, the Sea of Crises, and the Sea of Nectar here, Mare Nectaris. Now, the Sea of Nectar, you can actually see one of the outer parts of the impact basin there. So the full impact basin didn't fill with lava in this case, it was just the inner portion. So the impact basin for Mare Nectaris is that region there. And on this side of it, we've got cliffs that are about 1 kilometre high. So that's part of the outer edge of the impact basin that has Mare Nectaris in the centre. And let's look at a couple of interesting craters. You've got the crater here, Theophilus, quite a large crater, very deep, large central peak. It's really quite visible. You could see that with binoculars quite easily. One that's a little bit trickier to see though is the crater Messier, and it's one of the few craters on the surface of the moon that was caused by a very shallow impact angle. They reckon it was less than 5 degrees, so it almost skimmed off the surface of the moon. And if you look close up, it's actually 2 craters close together, probably because the impactor had split into 2 just before impact. And you can see the ejecta, rather than spreading out in all directions, they're mostly in the direction away from where the impactor came in and hit. So you can see the ejector mostly being this way, but it's also referred to as the lunar dragonfly or lunar damselfly, because if you think this is the body of the dragonfly, here's its head and thorax, and you can maybe just see some ejecta there forming the wings. Let's have a closer look at that. So there's the two impact craters. They are oblong in shape because of the shallow impact angle, and you can see the majority of the ejectors flow down this way. So the impactor come in this direction at the surface through material this way, but also through ejecta in this direction. So hopefully you can see there dragonfly's wings, dragonfly's head and body stretching out this direction. And there's a close-up from the Lunar Reconnaissance Orbiter of these impact craters. So they do look a little bit different to the normal ones that we've talked about so far. And there's a lunar map of the entire surface made up from images of this orbiter. You can find it via that website. So you can get these sort of detailed images. You can have a close-up look at the moon, even when it's cloudy. So I think that's a good point for me to stop and see whether there are any questions. So, and gents.
Yep, there's been a few come in, Gordon. There's one live at the moment, which is Mackenzie and Taylor are asking, where does the lava that fills the basins come from?
Okay, yep, that's a good question. The lava actually comes from below the lunar crust. So just like in the Earth, where the outer part of the Earth, you've got a solid crust, and then the deeper you go, the hotter the rock becomes, and if you go deep enough, it's molten rock or lava. You have the same thing on the moon. So if the impact is energetic enough, it can damage the crust deep enough down that it allows the lava to get from below up through the crust and then fill in the impact basin. Now, saying that, obviously, there will be some of the material in the basin and in the bottom of large impact craters that will be molten rock from the impactor itself. So it's not all going to be lava from down below, but for the impact basins, by far the majority is lava from below the lunar crust. So hopefully that answers the question. I see the next one, how's the moon made? Next talk tomorrow night. So I'm not going to go into it in detail, but there are a number of theories as to how the moon could have been made. One is reasonably commonly accepted, and I'll talk briefly about that tomorrow. So there you go. There's a preview to keep you listening for tomorrow's one.
Well, I hope that whatever you say is the same thing that I typed, which is what I got from Wikipedia. So there we go. So that's a different question's already been posed.
Right.
We've got some other questions that are coming in. So evidence of volcanic activity on the moon's surface?
There's nothing terribly obvious nowadays. There are things called volcanic domes. Are you able to see my cursor move about on the screen?
Yes.
Yep. There are some prominent volcanic domes, and one of the most obvious ones is up here. But even it is millions of years old. The recent mission by China to retrieve rock from the moon actually landed quite near to this zone so that they could recover some of this to see what kind of age the rock is in that region, and to give an idea of how long ago there might still have been some sort of volcanic activity there on the surface of the moon. But the moon is essentially geologically dormant now. So it's not like some of the other bodies in the solar system, such as Venus, which is extremely volcanic and active still. Did that answer the question? I forgot what the question was. I think it did, yeah.
So let's switch to one about the lunar orbiter and one of our favourite topics, Apollo. So we, Christopher and Ruben have asked, we heard that the lunar orbiter has got photos of the Apollo footprints and lander, etc. left behind. Is this true?
It is. If you were to type into Google lunar reconnaissance orbiter Apollo footprints, they have imaged at least 3 of the landing places for 3 of the Apollo landing places, and the amount of detail that you can see on the image is enough to pick out the leftover part of the spacecraft that launched to send the astronauts back to Earth. It has what looks like little trails on the surface that is actually the trails of the footprints of the astronauts as they've walked backwards and forwards, putting out equipment for experiments. And in one of them, you can actually see the lunar rover left behind. And now it's been there a while, so thankfully I don't think there's any parking charges on the moon for any vehicles that have been abandoned. So yes, I would recommend Googling that. You will find the images there, and they're incredible to see. Not detailed, but you can definitely pick those features out.
There's a question from Keith quite early on saying, Gordon, great photos. What equipment and software were you using?
I have a slide that I'm going to show tomorrow that will probably explain that better than I can in a minute or so here without actually pulling it up on the screen. So I would perhaps leave that one until tomorrow, and hopefully you can join in and get the details in. Okay. Next. I've kind of lost track of where we are in the questions. Is there?
Yep. So there was a follow-up from Christopher and Ruben after your comment about the Chinese lander. So why has China chosen to put their landers on the far side of the moon?
I suspect to get information from that side, because most of the missions so far have been to the side of the moon that faces the Earth. So clearly we know lots about this side of the moon, or the bit that faces the Earth the whole time. And I suppose it's good scientifically to get information from the unknown parts. Now, Keith might like to elaborate a bit more on that during his talk on Sunday evening. But I think by and large it's to get information from an area that we know less about. Okay, what's next on the list?
Microphone's off, sorry. So we've got a question from our Thomas asking, are the moon's poles colder than the lunar equator?
I think, I don't definitively know the answer to that. However, I don't think there's much of a difference between any part of the lunar surface that is in darkness or any part that is in full sunlight. Because there's no atmosphere there, as soon as the sun drops off of the part of the moon that it's lighting up, it becomes very cold very quickly. So the sunlit parts are quite warm by Earth standards, and the the parts in darkness are really rather cold. So the fact that the parts of the polar regions some parts will be in permanent daylight and some parts will be in permanent darkness. The bits that are in darkness will be permanently very cold, and the bits that are in daylight will be permanently quite warm. So it's not quite the same as what you find on the Earth, where the polar regions are just naturally cold because they spend lengthy periods in darkness because of the tilt of its rotational axis. The rotational axis of the moon is pretty much straight up and down. So hopefully that makes sense and sort of answers your question.
So more questions on geology. David Shand asks, is there evidence of tectonic plates existing during the moon's early history?
The moon's early history was 4 billion or so years ago, and although I've said that what you're seeing on the moon is pretty much the result of bombardment over those 4 billion years, I don't think there's any sort of plate tectonics happening, but I'm not a geologist. I'm just wondering, is Keith still there? Do you want to pitch in with an answer to that one, Keith? Because I think this is probably more your terrain, if you forgive the pun.
No problem, Gordon. No, it's a good question, and the short answer is no, there isn't. It's a very different type of body from the Earth. In fact, tectonic plates are quite unusual across the solar system. So if you think of the moon in its early stages as just a big ball of magma that gradually solidified and then was subject to subsequent bombardment of the crust that formed, that's more typical of the geology of the moon. So it's never really had the same tectonic plates that we see on Earth and the subduction zones and subsurface convection that drives that going forward. So it's a very different type of body from the Earth, and there's never been really real evidence of tectonics in the same way.
Okay. Now there was a much better answer than I could ever have given on that topic.
Well, time for one more. We'll sneak one more in. Back to space vehicles. Mackenzie and Taylor ask, is it more difficult to travel to and land on the dark side of the moon?
Probably no, but there are technical difficulties in that when you're on the far side of the moon, there is no direct communication with the Earth because the moon is in the way. So the actually traveling there is not any more difficult, but because you lose communication with the people on Earth, it's going to be more of an issue. And what you may have to have is a relay spacecraft where you can send the signals via to maintain contact with people on Earth. So actually getting there is not really any more difficult. The logistics of keeping in contact with the Earth is. Do you want me to answer that last one that I can see there very quickly? On the mountain ranges in the middle of the large craters from R. Thomas, essentially the middle of the crater, if you've got a big impact, the mountains in the middle of the crater are essentially caused by the crust rebounding as a reaction to the impact itself. So they're formed in a kind of slightly different way from the mountains round the rim, where round the rim it's the material in the impact zone being shoved to the side. But they are mountains still the same. It's just a slightly different mechanism. I'm seeing one more question there to do with why does the moon seem so big when it rises and gets smaller when it's higher up? the answer to that, if you Google moon illusion, so it's an optical illusion. If you Google that, there's lots of websites. Try to look for the reputable ones for an answer, such as the NASA ones or that. But you'll find the information for that one there. Okay, so that was good. That was quite a few questions, and it's always good to be able to phone a friend or bring the experts in for the difficult questions. So thanks to the rest of the team for assisting with them.
Thank you, Gordon. That was brilliant.
Oh, right.
Good evening, everyone. And thank you, Nicola, for stepping in at the beginning when my internet fell out. Thank you all for attending this evening, and a huge thank you to Caithness Astronomy Group for another fabulous and fascinating presentation. We can't wait to learn more about the moon over the next couple of evenings. Part 2 tomorrow night will be about the moon in motion, and part 3 on Sunday, the far side of the moon. Tomorrow morning at 11 a.m, we are welcoming back Dr. Michael Leach, who will be speaking about his experiences in Rwanda with a group of endangered mountain gorillas. He'll teach us how to get close to gorillas in the wild and how to communicate like a gorilla using body language and vocalizations. That is going to be a fun morning. On Wednesday, the 24th of March, Magnus Davidson from the Environmental Research Institute will join us to explore the offshore wind potential found around our beautiful coastlines of Caithness and discuss how new and existing developments can benefit us at local, regional, and national and international level. He will also look at the plans for the Pentland floating offshore wind farm off Dounreay and onto the wider potential for the new Scott wind leasing round. You can find out the full details of these events and the rest of the festival at science003.org. Thank you again for joining us, and we hope you enjoy the rest of the 2021 Caithness International Science Festival. Have a lovely evening, and thank you again. Bye.